Okay, in last lecture I told about normalization theory and then various types of normal form. As you all know, normalization theory is built around the various normal forms, and normalization is a scientific and systematic process through which we organize the various attributes among the different tables so that we can reduce the redundancy and remove the anomalies such as insert anomalies, delete anomalies, and update anomalies. And what do you mean by normal form? A relation is said to be in a particular normal form if and only if it satisfies certain constant. And in types of normal form, I have already explained first normal form. As you all know, first normal form is a relation in which multi-valued and composite attributes are not allowed, or a relation or table is said to be in first normal form if and only if all the underlying domains contain an atomic value. Very simple normal form, and by default all the tables which we create through SQL are in first normal form. Again, in second normal form, there should not be any partial functional dependency, or as per the CJ definition is a relation is said to be in second normal form if and only if it is in first normal form and all the non-key attributes are fully functional dependent on key. Now, in third form, a relation is said to be in third normal form if and only if it is in second normal form, and every non-key attribute is non-transitively dependent on primary key. Means there should not be any transitive dependency. In second normal form, we remove partial functional dependency, and in third normal form we remove transitive dependency. And suppose there is a relation R in which A, B, C are attributes, then if A determines B holds on R and B determines C holds on R. This is the FD set. There are two FDs which hold on R. Then from this we can find out the candidate key. Here candidate key is A. Why? Because A determines B and C. All the attributes of R we can determine with the help of A. A determines A itself also due to reflexivity rule. So A determines all the attributes A, B, C. So candidate key is A. And prime attributes is A. B and C are non-key attributes. Non-key attributes are B and C. Now, as per the definition, every non-key attribute is non-transitively dependent on the primary key. Here, B non-key attribute is non-transitively dependent on A, but C is not non-transitively dependent on A. C is transitively dependent on A. This is not allowed in third normal form. So we have to decompose this R with respect to this transitive dependency. Now we will decompose R into R1, and in R1 A and at which is determined by A, and in second table we will keep B and C. Now A determines B goes over here, and B determines C goes with R2, and now B becomes candidate key in R2. So in both cases there is no transitive dependency and there is no partial functional dependency. So we can say that R1 and R2 are in at least third normal form. Why I am saying that it is at least in third normal form? Because we haven't checked the constant of BCNF. Did you get it? Hello?
Yes, sir.
Okay. This is all about definition of any non-trivial FD. Suppose this is a non-trivial FD. Then for any FD, X should be either candidate key or super key should be prime attribute, then only we can say that R is in third normal form. This is the also a definition of third normal form. But if X is non-key attributes and A is non-key attribute, and non-key attributes cannot determine another non-key attributes. If this exists in the relation, then you can say directly this relation is not in third normal form because this is not allowed in form. Did you get it?
Yes, sir.
Non-key attributes are only determined by the candidate key. This is the definition of third normal form. Now, Boy's code normal form. Actually, it is proposed by two scientists. One is Raymond Boyce and another one is Dr. E.F. Cott. So we say it is BCNF, Boy's code normal form. And we can directly check whether the relation is in BCNF or not. Very simple definition. Every determinant is a super key or candidate key. As you all know, candidate key also a super key. Minimal super key is called candidate key. A relation is said to be in BCNF if and only if every determinant is a super key. Determinant. Suppose we write any functional dependency A determines B. Then A is called left hand side attributes or set of attributes is called determinant. This is called determinant. So as per the definition, left side of every FD should be super key or candidate key. Did you get it? Hello.
Yes, sir. Yes, sir.
So in third normal form, suppose this is not the candidate key and this is the prime attributes, then this is allowed in third normal form, but this constant is not allowed in BCNF. BCNF is more stricter form of more stricter than third normal form. And if any relation is in BCNF, then automatically it is in third normal form. BCNF is more strict than third normal form. Actually, first normal form we have less constant, then we increase the constant in second normal form, and then some more constant on third normal form. In third normal form there should not be any partial dependency and there should not be any non-transitive dependency, and then we increase constant in BCNF, and BCNF is a higher normal. Whatever redundancy due to transitive dependency occurs in third normal form, we can remove in BCNF. Okay, so here in this diagram you can see the things. Suppose relation is in BCNF, then here third normal form, and then second normal form, and this is the first normal form. So a relation is in first normal form, it may be in second normal form and may not be in third normal form. A relation in second normal form, it may be in third normal form and may not be in third normal form. But if a relation is in third normal form, it is in second normal form, and if it is in second normal form, then it is in first normal form. So suppose we check the constants and relation is in BCNF, R is in BCNF, automatically it is in third normal form. And definition of third normal form, a relation is said to be third normal form. First constant is it is in second normal form, and second, each non-key attribute is non-transitively dependent on candidate key or primary key. Hello, that's all about the definition of normal form, first normal form, second normal form, third normal form, and BCNF. Generally, questions of normalization is of two types. One is identification of the relation, whether that relation is in specified normal form or not, and second, if relation is in not the given specified normal form, then we have to decompose that relation up to that specified normal form. So for identifying normal form, we have to know the definition of all the normal form, first normal form, second normal form, third normal form, and BCNF. And each and every terminology related to normalization should be clear to you all. If you have any doubt related to any terminology, you can ask the question. Hello?
Yes, sir.
No, sir.
Now see here, suppose we have A, B, C, and here A determines B, and then B determines C. Okay, and if both are candidate key, left hand side are candidate key, then we can say that R is in BCNF. Then we will check every determinant of the functional dependency, left side of the functional dependency, and it should be super key or candidate key. Then immediately we will take decision R is in BCNF. So to identify relation is in BCNF or not is very easy, but you have to find out the candidate key. Find out the candidate key. And for finding out the candidate key, there is an algorithm, closure of an attributes. I will explain this in next lecture. Closure of an attribute through which we calculate the candidate key. For identifying the relation, whether it is in second normal form or whether it is third normal form, first step is to find out all candidate key of R. Then second step is we will find out prime attributes and non-prime attributes, prime attributes and non-prime attributes. and then we will check whether the relation is in second normal form or relation is in third normal form. Did you get it? Hello.
Yes, sir.
This is very basic
Yes,
concepts of normalization. And then I will solve various numerical problems which are related to normalization. Then you will understand the normalization concepts in more deeper way. Now see, this slide is related to functional dependency. I have already explained about functional dependency, but definition of functional dependency you should like this way. A relation R is said to have a functional dependency. Alpha determines beta, and suppose alpha, beta, gamma are attributes of R. Then we can say that alpha is a subset R equal to R. Why? Because in R, all the attributes in this set. So alpha is a subset R equal to R, and beta is a subset R equal to R. Here we can write like this: alpha is a subset R equal to R, and beta is a subset R equal to R. If and only if each legal relation for each tuple pair T1, T2, which belongs to R, satisfies that if T1 of alpha equal to T2 of alpha, then it must have T1 of beta equal to T2 of beta. This implies that if two tuples in any legal relation R are agreeing on the value of alpha, then those two tuples must agree on the value of beta. If this constant is satisfied, then you can say that alpha determines beta holds on R. I have already explained the meaning of functional dependency. Here you can say that functional dependency is the extension of the concept of key. If alpha determines beta, if alpha determines all the attributes of R, then you can say that alpha is a super key. And if alpha you can say that set of attributes. If set of attributes has no extraneous attributes, in that case you can say that alpha is a candidate key. Did you get it?
Yes, sir.
What I am saying?
yes, sir.
Okay. Now it is also related to functional dependencies, constants on the set of legal relations. I am not talking about illegal relations. And it requires that the value for a certain set of attributes determines uniquely another set of attributes. Here if we write alpha determines beta, then you can say that this is a set of attributes and this is a set of attributes. It may be alpha is a set of A, B, C and beta is a set of B, C. So here this notation represents the set of attributes. Okay. A functional dependency is a generalization of the notion of a key. Functional dependency is a generalization of the notion of the key. And in next slide, I will explain that things. Next to next. And here, trivial FD. What is the meaning of trivial FD? Suppose alpha is a set of attributes and beta is a set of attributes. And if beta is a subset or equal to alpha, then alpha determines beta. And this is for both legal and illegal relationship. There is no need to check this thing. If alpha is a subset of beta, then of alpha, if beta is a subset of alpha, then automatically alpha determines beta. Suppose we have a table student, and in table there are various attributes: roll number, name, and then date of birth. Suppose we have combination of roll number and name. If the combination of these two value is same for two tuple, then this value, that both tuples should agree on this name value also. If you are saying that combination of same in both the table, automatically part of this should be equal. So we can say that the combination of roll number student determines student name, or combination of roll number name determines roll number. And here also roll number is a subset of this set of attributes. Did you get it?
Yes, sir.
It is
Yes,
called
sir.
trivial FD. And in normalization, when we check the constants for each non-trivial FD, we will not check the constants for trivial FD. We will check the constants for non-trivial FD. Okay. So if beta is a subset of alpha, then alpha determines beta. Okay. There is no need to check whether these tuple pair agrees on their alpha value, and then automatically it will hold, and it will be satisfied by both legal and illegal relation. Then in next slide, I am trying to establish relationship between candidate key and FD. Please read carefully all the sentence. If K determines R and K is a subset or equal to R, then K is called the super key of R. If any set of attributes determines all the attributes of R, then K is called super key of R. If A belongs to K such that K minus A determines R, then we can say that it is extraneous attribute. If we discard A from K and that set determines all the attributes of R, then we can say that A is extraneous attribute in super key. And if we discard the set of extraneous attributes from K, then we will get the candidate key. If K dash is the complete set of extraneous attributes in super key K, then K minus K dash is a candidate key of R. And obvious, if K minus K dash is a candidate key, then K minus K dash determines R, or K minus K dash determines all the attributes of R. And a minimal super key is called candidate key. Now we can say that in this there is no proper subset which alone determines all the attributes of R. A schema R may have a set of candidate keys K1, K2, Kn, and all K1 is a subset are equal to R, K2 is a subset are equal to R, and Kn is a subset are equal to R. And what is the definition of prime attributes? If any attributes A belongs to either in K1 or in K2, like it should belong to at least one candidate key of R, then we will say that A is prime attributes. If any attribute doesn't belong to any candidate key of R, then A is non-prime attributes. So in this way, mathematically we can define key attributes and non-key attributes. And if we'll take the union of K1, K2, Kn, then here if we are saying कि A belongs to union of K1, K2, Kn, so A either belongs to K1 or belongs to K2 or belongs to Kn. And if A doesn't belong to any candidate key of R, then that A is non-prime attribute. See in this slide, an attribute A belongs to R which doesn't form any of the candidate keys of R is called non-prime and non-key attributes. And in normalization, this is very important. We have to segregate attributes in two buckets. One is key attribute bucket and another one is non-key attribute bucket. And then we verify the constants of second normal form, third normal form. Did you get it? Hello.
Yes, sir.
Yes, sir.
Now see this definition, left irreducible FD. What is the meaning of this? If we write alpha determines beta, and if there is a proper subset which determines beta, then this is not left irreducible FD. If there is no proper subset in alpha, then we can say that this is the left irreducible FD. Read this thing. If FD alpha determines beta, there is no alpha 1 which is the subset of alpha which satisfies alpha 1 determines beta, then alpha beta is called left irreducible FD. Means we can't reduce the left part of the FD. This implies that alpha doesn't have any extraneous attribute. If K determines R is left irreducible FD, then we can say that K is candidate key. Did you get it? Hello?
Yes, sir.
Yes, sir.
Otherwise, K is super key. Minimal super key is called candidate key. Okay. Now, see the second paragraph. This is very important paragraph. And try to understand the meaning of this paragraph. Set of FDs holding on a schema R. A set of FDs is said to hold on a schema R if each FDF belongs to capital F, is satisfied by each legal relation R of capital R. This implies that if F is the set of FDs holding on a schema R, then a relation R would be legal only if it satisfies each FD F belongs to F. Now see here. Suppose we have an relation A and in which we have 4 attributes. And on this relation there is a FD set in which these are FD set. Okay. Now if a relation R of R satisfies all the FDs which we mention on FD and these FDs hold on R, then we will say this relation is legal. Otherwise, this relation is illegal. Did you get it? Hello?
Yes, sir.
When will we say this relation is legal and when will we say this relation is illegal? If relation satisfies all the functional dependencies which hold on R, then we will say this relation is legal. And if relation doesn't hold any FD of the FD set which we define over R, then we will say that relation is illegal. Okay. If we relate this thing with the real world problem, Then suppose you have a family, and in family there are various relation, husband wife relation, son father, daughter father relation. These are legal relations. Why? Because this is defined by the society. But some another relation sometimes established and that is not defined by the society, then we will say that that relation is illegal. Did you get it? Hello.
Yes.
Only that set of attributes will be legal which satisfies these functional dependencies. Otherwise, we will say that this relation is illegal. Okay. Now, see this slide. What is the meaning of logically implied functional dependencies or logically inferred functional dependency? This is not on. Logically implied FDs or logically inferred FDs. Again, see here, if we have a relation R A comma B comma C and we have a set of FD on this relation, one FD set is A determines B, another FD set B determines C, then this is the set of FDs. Hold on, this R. Now, if we derive another FD set from this existing FD sets with the help of Armstrong's axioms, I will explain that Armstrong's axioms are inference rule. If we derive new FD and that FD is satisfied by relation, then we will say that this FD is logically implied FD or logically inferred FD. It. Hello.
Yes, sir.
Here A determines B and B determines C. Though A determines C is not mentioned in this set, but logically we can infer this FD through transitive relationship. So this is called logically implied FD. Okay. So there are various rules: augmentation rule, union rule, reflexivity rule, transitivity rule. We apply on this set of FDs, and whatever another set of FD we achieve, that is called logically implied or logically inferred FDs. Okay. Now, closure of FD set. What is the meaning of closure of FD set? Suppose F is the set of FDs having on R, and F dash is a complete set of FDs logically implied by F. Then if we take union of both F union F dash, then that is called closure of FD set F. In previous slide, F is A determine B and then B determines C. And in F dash, logically inferred FD is A determines C. And if we take union F dash, then that is called closure of an FD set. Did you get it? Hello.
Yes,
Yes,
sir.
sir.
But here complete set of FDs logically implied by F. This is not the complete set. And in complete set, both trivial and non-trivial FD. I am talking here trivial FD and non-trivial FD. So this is the non-trivial FD, but there are various trivial FD also, and we will consider over here. Like A determines A through reflexivity rule. A determines A. B determines B. C determines C. Okay. Then A determines phi. B determines phi. In this way, all the trivial and non-trivial FDs logically implied by these existing FD sets, and then we combine both F and F dash, and then we will get closure of an FD set. Means in this set, all the FDs we mentioned in this closure set are closure of FD set F. Okay. Then another terminology, cover of an FD set, and question has been asked on this topic in GATE examination and AK2 examination. So first, understand the concept of cover of an FD set F. See here, an FD set G is said to be cover of an FD set F. There are two FD sets, one is G and another one is F. G is said to be cover of an FD set F if F is a subset of closure of G. First we will find out the closure set of G, and if F is a subset of that closure set of FD set G, then we will say that G is cover of an FD set F. This implies that closure of G contains FD set F. Did you get it? And if G is a subset of closure of F, then we will say that F and G FD sets are equivalent. If F is a cover of G and G is a cover of F, then we will say that F is equivalent to G. Did you get it? Hello.
Yes, sir.
In next slide, you all will say equivalent FD set. Two FD sets F and G are said to be equivalent if both form cover of each other. F is a cover of G and G is a cover of F, then both are equivalent, F and G. Okay. If F is hold on R, then all the FD sets of G will also satisfied by R. If all the FD sets are held by R, then all the FD sets of F will be satisfied by R. Why? Because both are equivalent. Both are equivalent. Did you get it? Hello.
Yes, sir.
Yes, sir.
These terminologies are very important. Unless until you don't know the definition of these things, you cannot solve the problem related to these topics. And I will explain the numerical problem related to these topics. Then you will understand these concepts in much deeper way. Did you get it? Now,
Yes, sir.
canonical cover of FD sets. Very important topic, and question related to this topic has been asked in GATE AKTU examination and in GATE examination. In question, set of FD given, and you have to find out the canonical cover of FD sets. So for finding out the canonical cover of FD sets, there are 3 steps, and you should know all these steps, and then we will find out the canonical cover of FD set. A set FC is said to be canonical cover of an FD set F if F is a subset or equal to closure of FC and FC satisfies the following 3 conditions. Each FD in FC set has only one attributes on right hand side. Suppose if any FD holds on R, alpha determines A, B, C, D. Through decomposition rule, we can write A determines alpha determines A, alpha determines B, alpha determines C, and alpha determines D. But if we have any FD like this, then we can't write this thing. Please note it down. Beta determines A and then C determines A. We can't write this thing. But if we have alpha determines, and here if set of attributes on right hand side, then we can write like this: alpha determines A, alpha determines B, alpha determines C, and alpha determines D. So this is very simple steps, and student do first step very easily. Then second step, all functional dependencies in FC must be left irreducible form. If not in this form, then we will convert left hand side into left irreducible form. There should not be any extraneous attribute. If extraneous attributes present in left hand side, we will discard that. And in third, there should not be any extraneous FD in this FD set. If any extraneous FD is in this FD set FC, then we will discard that FD from that FD sets. And extraneous FD means the FD which is logically implied by other FD sets. If any FD is logically implied by existing FD sets, then we will discard that FD sets from the FC set. Then whatever we get in FC, that is the canonical cover of FD sets. Did you get it? Hello?
Yes, sir.
Yes, sir.
Now I hope that you all understood the terminology extraneous, logically implied, closure, and then canonical cover. And another topic is closure of an attribute set. This is very important algorithm, and through this algorithm, closure of an attribute set. Through this algorithm, find out the candidate key. So in normalization, first step is find out all the candidate key of R, and then segregate attributes into 2 buckets. One is key attributes and set of non-key attributes, and then we will verify whether R is in specified normal form or not. Closure of an attribute set. Very simple algorithm of closure of an attribute set. Suppose alpha is the set of attributes, then closure of an attribute set is represented by alpha plus, and alpha plus is the set of attributes which are determined by this set of attributes alpha. Closure of an attribute set means the set of attributes which are determined by this alpha, and that is called closure of an attribute alpha. And if alpha plus determines all the attributes of R, then we will see that this is the super key. Did you get it?
Yes,
If
sir.
alpha plus determines all the attributes, then we will say that alpha is candidate key. And if there is no extraneous attributes in this set of attributes, then that alpha is called, please let me know. Hello. If there is no attributes in alpha and that determines all the attributes of R, then that is candidate key. Did you get it?
Yes, sir.
Yes, sir.
If alpha plus determines all the attributes of R, then it is super key. And if there is no extraneous attribute in closure set of alpha, then that
Candidate
set is
key.
called candidate key. And in next lecture, I will